mistake with me. Ah, the arrogance of youth. Well, times have changed, and I've come to see that old Al was really a pretty smart guy. I'll bet you're wondering how we know this prediction is right. I mean, has anyone ever tested it? Well, we have. GPS satellites would not work accurately enough if we didn't adjust for how their high speed across the sky causes their clocks to run slower. But let me give you an example from particle physics that proves that an observer who sees an object moving experiences a longer amount of time than a person who sees the object as stationary. So I'm a particle physicist by trade. One of the things we do is make beams of particles that go at very high speeds. The details of how this is possible aren't very important here. Okay, to illustrate how time depends on a particle's speed, let's talk about a specific kind of particle called a pion. Pions are very easy to make. We make tons of them. Now, it turns out that pions are unstable, basically like radioactive materials, and they decay into other particles. So what we do is make stationary pions and measure their lifetime. It turns out that stationary pions live for about 26 billionths of a second. This is all well-established science, and we've known about pion decay since the late 1940s. Now suppose that we shoot the pions with a speed of 99.9% the speed of light. That means the pion will be traveling 300 million meters per second. If relativity wasn't real, a particle with a lifetime of a pion traveling at that speed would travel 7.8 meters, or about 25 feet. It turns out that creating a high-speed beam of pions isn't that hard to do. What does relativity predict? It predicts that the moving pion will live longer. Its lifetime won't be 26 billionths of a second. Its moving lifetime would be 582 billionths of a second, and it would travel 174 meters, or about 557 feet. So we do the experiment, and what do we find? Do pions travel 25 feet and decay, or do they go 557 feet? The answer is 557 feet, just like Einstein predicted. So there you go. Classical physics makes one prediction, special relativity makes a very different prediction, and special relativity is right. And that, as they say, is that. Time isn't the only thing that is different for moving and stationary objects. While the time experienced by a person seeing a moving thing is longer than for a person seeing a stationary thing, the physical length of the moving thing is shorter, but only in the direction of motion. That means if you have a ball that's a perfect sphere when it's stationary, and you give it a speed that's a significant fraction of the speed of light, it will look more like a pancake to someone seeing it flying by. It's hard to measure this effect directly, but it turns out that if you combine Einstein's theory of relativity with Maxwell's equations, the unification of electricity and magnetism gets much deeper. In Maxwell's equations, the two ideas are inextricably tied together, but still distinct. When you add relativity, the distinction evaporates, with moving and stationary observers disagreeing about the amount of electricity and magnetism, and the two phenomena become truly indistinguishable. All right, so let's change from space and time to mass and energy. In Einstein's miracle year of 1905, he wrote 4 seminal papers. One of them was on what we just talked about, the way space and time blend. But the other one showed the deep connections between energy and mass. In a very real way, his theory unified these two seemingly distinct concepts. Perhaps the most famous equation in physics is Einstein's equation, E equals mc squared. It's also among the most misunderstood. So first, let's interpret the equation as it's usually done. The symbols we see are E, which stands for energy, m, which stands for mass, and c, which is the speed of light. So in words, it says that the energy equals mass times a constant, specifically the speed of light squared. A constant is basically just a conversion factor, like converting feet to inches if we multiply by 12. So the equation essentially says that energy and mass are the same thing. You can convert one into the other and back again. So one question is, how much mass equals how much energy? The answers are surprising. Let me illustrate with a particular example. Suppose I wanted to convert a gram of matter to energy. A gram is about the size of a paperclip. So how much energy do you think we're talking about? The energy carried by a mosquito? The energy of a sneeze? A hand grenade? Enough to melt the entire planet? It turns out that the energy equivalent of a gram of matter is about the same as the atomic explosion at Hiroshima. A little mass is a huge amount of energy. Mass is simply ultra-concentrated energy. Now, I should caution you. People misuse E equals mc squared all the time. It's easy to do. For instance, I've received letters from people who know that photons have energy, and then they use Einstein's equation to calculate the mass of a photon. But photons have zero mass, so that's clearly a problem. So, I want to let you in on a little secret. The equation E equals mc squared is actually wrong a lot of the time. Well, it's not exactly wrong. It's just that that particular